G'day everybody and welcome back. I'm just getting this board finished, but I just wanted to mention something. On this board, two of the transistors are around the wrong way. I'll leave a comment in the last video, and I'll put it in the description, because I don't want people to copy that and get it the wrong way, and I also don't want people to worry for me, thinking that I'm about to smoke. Oh shit. That was not good. Dumb shit I do. Yeah, so I don't want people to worry and think that I'm about to smoke some transistors either, so I'll leave a comment. Make sure that leg's not about to rip off. No, I really got lucky there. Anyway, I'm just getting this board finished, and then we will get on with the rest of the amp. I've just got to swap those two transistors around the wrong way. See, the thing is with this board, the MPSA 92s, the PNP devices that go on this side, they need to go facing the opposite way. I'll show you after I've put this one on. And I don't know what's happening today. This is not going to plan. That'll do. Yeah, that'll do. Okay. Yeah, it's alright. I was looking at the clearance, umming and ahhing about it, but it's alright. So you see that's facing this way, those are facing that way, because the collectors have got to be on this side, not both on the left. Sorry, I just realised that probably didn't make much sense the way I was gesturing. Perfect. Sometimes I get them first go. Alright, well, I'll stop recording and I'll get this board finished and change these transistors. Actually, I'll change these transistors straight away, just so that there's absolutely no chance that I could forget, because that will really be bad. Not just for these little transistors, but literally for the entire amplifier. It would just be a really terrible thing to have happen. You know what? I was just looking at that going, it's a bit dirty, that solder. I need fresh solder, but I can clean this by adding some flux. It always gets blocked up if I don't use it for a while. Oh my goodness. Really? This works so good when it works, but if I don't use it for like, I don't know, a couple of weeks, it does take a while, but the thing is that does happen frequently, that I don't need to use liquid flux all the time, you know, and then this happens. Let me just go get a resistor or something. Alright, that's that problem solved. See, it literally just runs out. Works really, really well when it's not blocked. Actually, I need some up the top too. Literally just runs out. I guess I've got the focus lock on, you probably couldn't see that. Anyway, let's get these on quickly. This is really awkward. I got it. Just flow a little bit more solder in there to make sure that that's all flowed, because it did get a little bit unfresh. Alright, now I've just got flux residue to clean up. Get this other one in too. Alright. I'll just do the same thing with the solder. Okay, now that board's finished, I'm going to have to clean the flux off again, but anyway, I'll clean this up, get that board finished, and then we'll continue with building the amp. That's that board nice and clean. Actually looks quite nice. Alright, I'll get this board finished and then we will continue with building the amplifier. I think we will be doing a little bit on the power supply, but I'm going to get started on the front end. Alright, that's both the driver boards done. There they are. And yeah, I did notice a couple of things wrong. I'd put diodes around the wrong way on the board I was just working on. I've corrected everything now. If you have a good look at it, you'll see that everything is correct. All right. Okay, so last night I did some maths and I gotta say, I kind of messed up. So I wanted actually literally about this much more microfarads per rail. Pretty much I have always been comfortable going basically 10,000 microfarads every 100 watts. Now, I'm trying to get 250 watts here at 4 ohms. I want my, 25,000 microfarads. I did the maths on this. It's what? Let me tell you exactly what it is. It's only a little bit shy, but the thing is, the way I see it, capacitors age. And if it's already a bit shy now, it's only going to have higher ESR and be shyer in the future. I guess ESR is not really a problem because of how many capacitors I've got stacked up. But, let me just put this in the calculator. 4,700 times 5, 23,500. So, it's only short 1,500 microfarads. But then you could look at it this way too. That's short off the line. If I wanted to add a little bit of margin, say 20% headroom, it's short by about one of these. So that's how I come up to that conclusion. The other thing I wanted to do, these MKTs that I've added, I just want to put one more on each rail, so there's two. So I'm just going to, fold the legs over the end of the board here and put them like that. And I'm just going to do the same thing with the capacitors. I do have a little, here's the other thing I was considering doing. I was considering this last night. I was considering taking a strip of PCB, cutting it like this, etching some lines onto it, and then, soldering some of this copper wire, like a few pieces, to connect it. And I thought about it, it's just, there's no point. I might as well just do what I just said. It's just, yeah. So that's what I'm going to do. So I'm going to get that done now. Then I'm going to go over, you know what, I'll go over it now. Let me just go get what I want to talk about. I have made some changes to the power supply. So I had these heat sinks, so I just grabbed one for reference. I had these two big heat sinks for the rectifiers, but they're a little bit too big. I've got these heat sinks, which incidentally came out the same amplifier that the transformers and heat sinks came out of. Now these had, two 25 amp rectifiers or something like that mounted on them. But I'm just going to drill a hole in the middle on this higher piece of plate and stick one on each one and mount it to the bottom of the case that the amplifier goes in, if that makes sense. So it'll literally be like that. Or I might do it like that actually. No, I'll do it like that. I think I'm going to get better thermals like that because there's a shorter area to the case, but then there's still a fin to get any heat out that's not getting transferred into the case. So I feel like that's the better way of doing it. So I'll do it like that. So that's what I've done for the heat sinks. Still going with the 35 amp bridges. I've just dropped a switch on the floor. Those are the power switches I'm going to use. Now, the capacitors I had across the transformer, they were 0.22s, 220 nanofarad. I've gone a bit smaller down to 0.1. The reason for this is it's not a switching supply. I'm not using the capacitors for power factor correction. I've actually done the maths on this. If I wanted to put a capacitor across a transformer this big for power factor correction, I'd need about 40 microfarads. Actually 41.5 is what the math came out to. That's insanity. That's not going to happen. So the only purpose that's going to do is sort of act as a little bit of a filter, for transient spikes and stuff like that on the mains. So I've just gone down to 0.1 because 0.2 is just consuming more power. It's got AC passing through it. It's just a waste. Now, the other thing that I've done is decided upon these components. I think I might have already gone over this, but I'm not sure. There's going to be these 100 nanofarad green mylar capacitors over the secondaries of the transformer. Now, the reason I've chosen these, I guess a lot of amplifier manufacturers and power supply manufacturers and stuff like that know the answer to this question, but a lot of DIY hobbyists probably don't know the answer to this question, so I'm going to let you all know. Because this is something that over years of designing power supplies and stuff like that, I've actually realised this with my own research. So I answered the question myself. Now, people always ask, how come there isn't an R and a C forming a snubber over the secondary? Good point. Depending on the type of capacitor, you probably will need an R. So the thing is with snubbering with a capacitor, the R gives you your damping factor, or adds a damping factor to it. You already have a damping factor, but it adds a damping factor. Now, these capacitors happen to have an already high ESR. So it's basically like there is a resistor in series with them. That is why, in a lot of situations, only for small damping situations, you can just put one of these straight across the transformer. If you had a lower ESR cap, you probably would want to use a resistor in series, if that makes sense. How did I discover this? By building snubbers to get rid of common mode noise and trialing different types of capacitors. And I noticed that certain types of capacitors, the resistor value ended up going lower and lower until it became 0 ohms to get the best damping effect. And when I measured all the capacitors, that turned out to be the capacitors with the higher ESR. And when I thought about it and made sense, there is more resistance in series. Hence, no need to add a resistor. So that's why I've chosen them. We've already gone over that before, the 5 ohm, what do you call them? Negative temperature coefficient, NTCs. I don't know that they can handle the current. I don't have a data sheet for them. Actually, you know what? When I finish talking about this, I'll have a look and see. I should be able to find a data sheet for one of them. I'm pretty sure they're the same part, just different manufacturers. So I'll have a look. But that's for my inrush current protection. Because I've got such a massive cap bank, huge transformer, you know, I'm expecting a pretty big inrush current. I don't want to have to oversize the main fuse to a point where it's not a fuse anymore. So I want inrush current limiting. Now, I will be doing tests on this under load and having a look at the volt drop on them and how warm they get, all that sort of stuff. And, you know, if it's not going to work, I'm not going to do it. Other thing is the capacitors that you see here. These are 1 kilovolt ceramics. They're 10 nanofarads, and they're to go across the switch for arc quenching purposes. So when you turn the switch on and off, especially off, not so much on, I guess. I mean, there is a little bit that happens when you turn the switch on, but it's literally bugger all when you turn it off and you get that kickback, especially when you got a transformer or something on it. You get a huge arc, and that basically takes away your surface area on the contacts. Not surface area, I'm having a blank day today, I can't think of words. The stuff that it's electroplated with, whatever the contact surface is. It might be gold, it might be silver, it might be chrome. I can't tell you, I'm not a switch contact expert, I don't know what they use, but they usually use a piece of brass or something like that and then plate it with something else that doesn't arc as much and also has really low contact resistance to make the switch last. So you don't want to destroy that with arcing. So that's what these help with. Alright, well, I'm going to get to making this little bit up, and I'll go put these components back away now that we've spoken about it. But what we're going to do is make them up, and then I'm going to put all the power supply together. Might build another board or two for the power supply. I haven't really thought about that. That's basically what I'm going to get to now, is I'm going to put these capacitors on the capacitor bank, and then I'm going to have a think about the power supply, specifically the input section and the output section of the transformer. There's just a little bit of circuitry, so I might make another board. I really wish I had thought about that last night, because I wouldn't have made those on a single board. Although actually, now I think about it, that's probably not such a bad idea, because I can run the AC line in the back of the case, screw this down, mount it down to the case, and have the active go straight for a fuse at the back of the case to the switch at the front with a little arc quenching cap across it. And then from that, I can go to the transformer and NTC and capacitor. So I guess I'll have to make a little board for the NTC and the capacitor. Then on the secondary of the transformer, where it goes to the bridge rectifier, that's the... Let me just think about this here. Because you've got your two ends of the winding going to each side of the bridge, but your ground wire goes straight to the bank, or center tap, should I say. So these capacitors, these mylar caps, need to go across center tap to the end of the winding on each side of the transformer, on each of the secondary windings. I might make a little board up for that too. I think I will. Actually, yeah, I've come up with a really good idea. That little piece of strip that I just showed you before, I'm going to use that. I'll just cut it into a couple little pieces of strip, and I'll cut the wires fairly short coming out the transformer and solder them onto the strip, so it's like a transformer with a tag plate on it, a tag strip, something like that. And then that'll give us a spot to solder capacitors and more wires to go to the cap bank and rectifiers. Alright, well, I have my plan, so I'll go execute that now and then come back and show you what I've done, and then we'll cobble the power supply together on the bench and get this all put together and start setting the bias, and then we'll go from there. Now that is an audiophile grade capacitor bank. Anyway, I'm happy with that. That looks awesome. So there is actually one other circuit that I need to build before getting started on the front end and putting the amplifier together. Fan control circuitry. I completely forgot about it. Now, I also have to work out what I'm going to do with the fans. I remember when I built one of these amps a few years ago on this heatsink. 500 watt, same thing, same deal, 250 watts a kernel. I remember using one fan. And I remember having said fan in the middle of the heatsink. I'm just getting a fan to show you what I'm talking about. I had it like that. I think actually I might have had it that way. No. I had it that way. That's all right. Yes. I was sucking air in and blowing it through the heatsink, going in the middle and out. And there was a bit of air coming out here and most of it shooting out the sides. That worked really well. Also, you got to remember with the diode sensing for the thermals, you don't want to move air in a funny way that upsets it. I don't know the best way to explain that. You don't want to artificially cool one area of the heatsink more than another, because the diodes will sense it and think that that's what the transistors are doing, is what I'm trying to get at. So I think that's why I did this, because, well, in my mind, the only there's three ways you could go about doing this. You could build a shroud, or you could have both the heat sinks sort of forming a tunnel like this. You can put insulators between them if you want, and have, you know, a fan at each end, or just one fan at one end. That's one way of doing it. The other way is like I showed, or like this. So I still have to come up with what I want to do. I don't know yet. I haven't decided. So that's what we're going to do now. I'm going to decide how many fans, where they're going to go, all that sort of stuff. And then we need to devise a fan speed control. I don't want the fan just running full speed when it gets to some set temperature, because it could get to said set temperature with the volume down quite low just from running over a period of time, and then all of a sudden you're going to have this huge loud fan, right? That's not a problem when you're blasting music, but you don't want it when it's low. So fan's going to be on speed control. So that's what we're going to do now. Alright, so I'm sorting out components for the fan speed controller. Now, I've decided to go the linear route. I've already done some tests here. I sat here with 15 volts coming in, because the transformer the transformer for the amp's got an extra secondary that supplies somewhere in between, I don't know, 20, it's around 20 volts. That's going to power a 7815, which is going to supply this with 15 volts. Now, it's very simple for me to do this linearly with a couple of components and it will cost nothing. Yes, it wastes a little bit more power than doing it PWM, but it's such a small amount of power, I really don't care. Also, if you think about how much power I'll be consuming at the point when the fans come on, it really doesn't matter. This is a 1000 watt amp, 500 watt amp. You know what I mean? So I'm not worried. So what I've done, these are TO220 13005 transistors, not 13005D, just 13005. I do have the D variant. It's got a diode across the collector emitter pins for protection. I'm not going to waste that transistor because I don't need it. I put the fan in the collector path, so I don't need a diode here. This will do fine. This is a high voltage transistor too. These are cheap as chips, so that's the main reason why I've chosen it out of all the stock I have. It's just a good transistor to do this. This package can dissipate 75 watts. Even if they've cheaped out and put the 40 watt die that goes in the TO126 package in here, these cheap Chinese transistors, you'd be surprised what I've seen. It's still plenty for the job. I don't think it is a fake, but you never know. I've come across a lot of 13003, 13005, and their variants that are faked. And I pulled them literally out of boards. So, yeah. Anyway, for this circuit, more than enough. I had these two really shitty heat sinks lying around, and now I'm questioning how shit they are. Well, they are shit because they're not even straight. Like, this is how I bought them, and they weren't straight. But the thing is, they're so thin, it just looks like rubbish. But the thing is, I just sat here. Let me go get the heatsink I was using. I just sat here with these heat sinks, which are nice and thick, as you can see. It's a bit of a joke. Anyway, I sat here and I ran the fan at half the rail voltage. It's coming in 7.5 volts to see the maximum dissipation on this. You know, feeding 8.1 volts into the base of this with the power supply. To see how hot it would get. And I had it on this, and these got really, really hot. I mounted it to this, both the transistor and the heatsink are just running warm. So it's quite interesting. The thinner aluminium, it seems to wick the heat into the air more efficiently. So it's quite interesting. Small heatsink design's an interesting subject. The thing is, these are $1.10 for a packet of, get this, 10 off of AliExpress. You know, so they're supposed to be made to be crap, but they actually work really well. I just thought that was funny. Usually crap stuff is crap. Anyway, so I've got the 13005 on a heatsink. In the collector path, we've got the two fans. The emitter's going straight to the rail. Now, I might end up changing that, but I'm not worried. It's a dumb thing to do because if you don't limit the base current or limit the emitter path, you can, you know, kill the transistor if something goes wrong. This circuit is a kind of a dangerous circuit, but it works really well. And the thing is, if you get a component failure, like I think if this goes short circuit or a few things like that, you know, it can destroy the transistors, but the likelihood of that happening is like zero, as you'll see when we build the circuit, just due to the components we use, the way they're set up, all that sort of thing. So in actuality, it's actually a good circuit, even though it looks bad on paper. So I'm going to show you what I'm going to do. I'm going to put, oh, by the way, this is Darlingtoned up with this little BC549 because we need a lot more gain than what if we've got a gain of 100 or whatever. So now we've got, say, a gain of 1,000. And I'll just show you, if I put this between collector and emitter, the fans aren't coming on. But with a gain of 1000, they're on. Now if I warm this up with my hand, don't know if you can see that or hear it. Alright, that's already speeding up. This NTC's got a really nice temperature curve on it. I worked that out playing around with a circuit earlier. I was playing around with a PWM circuit and it just didn't work good with these fans. It made a noise that wasn't nice. The circuit just didn't behave the way I wanted it to. So I've gone back to this. It's sort of the amount of components it was taking to was getting annoying. Anyway, so what I'm going to do now is, well, by the way, the power supply is turned all the way down. So if I turn the voltage up to 15, yeah, that's how the fans are running. They're running about, I'd say that's around 12.5, 13 volts. It sounds like. Let's have a look at that. Oh, 11.5. Yep, that's with the power supply on 15 volts. So now what I've got to do is I've got to bias this down. So the thing is, I might not just do that too. We might end up biasing it in both directions, putting some resistance across it. But with this circuit, you need in between 1 and 3 resistors to get it to behave the way you want it to behave. It's with the components that are here on the board, and you just can't beat the simplicity of that. So I'll go get the first component and show you how to dial it in. So these aren't my pots for stock. All my potentiometers for stock are in the drawers over there, where you see just under the SMD boxes. Anyway, I also have these. What I've done over the years of building stuff, every time I've needed to dial in a voltage or switch stuff in and out, I've left the leads on all these things and put them in boxes, in a box basically. So now when I go prototyping, I need a 100k pot. 100k pot's already got wires on it ready to stick in the breadboard. I just need 2 in this case, the wiper and 1 into the track. Bada bim, bada boom, ready to go. So this is a 500k pot. I might just get a resistor and put a resistor in the little man, I'm trying to work in here. Let me get the cat out, sorry. Alright. Little man always wants attention. Instead of going straight from positive to the base with that, let's put a resistor in series with it. Sorry, so you need 4 resistors. At maximum 4 resistors in the circuit, minimum 2. Let me go get a resistor. Alright, so for this purpose I'm starting with a 10k resistor. That will suffice more than enough to supply current. Bear in mind this NTC is over 100k. 10k is a tenth of that, so it's actually less than a tenth of its resistance. So it won't make a noticeable difference with a gain of 1000 with the transistors. So we have that. Now we can't blow up our pot. So we'll get the fans to a speed I'm happy with. And let's see how the circuit behaves when we give it heat. Actually, so you guys can understand better, not understand as in get what's going on, I'm sure you get what's going on, but actually see the speed of the fan, not in RPM, in volts. I guess it's easier for you to look at it on the screen than to just listen to the fan. Oh, that's right, that clip's broken. I'll have to fix that. Let's see if I can get on this leg. Yeah, that works. Alright. So, got it round the wrong way, doesn't matter. Got 4.5 volts there. 15 volts coming into the circuit. Let's give it some heat. And that is how you build a really simple speed controller. You can't beat that. So now what we have to do, like I said, this NTC's got a really good temp curve on it. So if it doesn't have the temperature curve you want on it, you end up bringing more resistors in. You can put a resistor between the negative rail and the other side where the base is of it to bias it down a bit. That sort of kills some of the gain, if you want to think of it like that. You can put a resistor across it to lessen its effect on the circuit. You can play around with 3 different resistors to try and make it better, if that makes sense. Anyway, I'm happy with what I've got. So the next thing we've got to do, we need to see, can the fans reliably start at 4.5 volts? I'll show you what happens if the voltage is too low, why I say reliably start. So that's a yes. But let's go down to I have never seen 12 volt fans start running that low. That's quite surprising. Alright. Alright. So you see how one started but not the other? But if I kick it over, it'll go. This is what I mean about there being a voltage where it won't reliably start. So if we now take the power away and then bring the power back, you see the problem? That's not reliably starting. Now, if it can still end up starting at 2.4 volts, we know 4.5 is fine. So let's go back to 4.5. It's going to be very tricky to get it exactly there because we're right down the end of the pot. But what we do now is we get it set to 4.5 volts. I'm actually going to go for 4 volts. I'm happy with that. No, I'll go for 4.5. I'm happy with that. That's a good speed. And the thing is, you got to take into consideration, the other thing you got to take into consideration with this circuit is when that's on a heatsink, it's probably going to sense a cooler temperature. Well, not when the transistors are biased, but just when it's on there. And what time of the year it is too, because the ambient temperature will change. So you don't want to set it at too low of a voltage. You don't want to set it at too high of a voltage, if that makes sense. You know, if you set it too high, when you get into a hotter time of the year, the fan will be too fast, too loud at low speed. If you set it too low, well, you're going to have the opposite problem at the other end of the year. So I hope that makes sense. So the only way you can blow up transistors is by shorting this, or if it was to fail short. Now, in this case, it wouldn't, because there's a 10k resistor in front of it. And even if the transistor's got the amplifier's heatsink, like the amplifier's output stage itself, even if that went into thermal runaway and blew up, got really hot, this can't drop in resistance low enough because it's 120k. It will only be in the, kilo ohm region. A few kilo ohms, maybe hundreds of ohms, but won't get low enough with that 10k resistor and that to supply enough current to turn the transistors on enough to just sink current through the base to emitter junction and pop it. So that's what I'm saying. That's why I was saying the circuit kind of looks silly on paper, but when you think about it, it's actually perfectly fine. And I've never had one of these circuits fail. I have made the transistors pop by accidentally shorting over this whilst literally breadboarding it, but that's all. Anyway, so now what we're going to do is we'll turn this off. We'll take this out and we'll measure the resistance between these 2 points. And then you guessed it, we'll sub that out with a fixed value resistor. Always remember, when you're measuring a higher resistance, to only touch one wire because your body will have an influence. Well, you can't get luckier than that, can you, when it's bang on a stock value. 22 kilo ohms. I know I'm making this look too easy. I'm sorry, guys. Yeah, I've been building stuff for a long time. It happens like that. Let me go get a 22k resistor. One 22k resistor. That goes from positive to here. Did I just measure? Oh, no power. I thought I might have. Okay. What on earth have I done? I don't think that was 22k. I think I measured the wrong side of the pot. Oh, man. Wait, did I just put that? I know what I did, never mind. I put the resistor in the positive rail, didn't I? Yeah, it was 22k. Oh, that's funny. That's 5 volts. I'm going to go get an 18k resistor. We'll give that a go. Or is that coming down? Oh no, that's correct. So there you go. And we can simplify this circuit a little bit more by taking out one wire. There you go. You're not going to make it any smaller than that. So I'm done. Now all I need to do is get a little bridge rectifier, some capacitors, 7815, slap that and this together, and that, well, times 2. How am I going to mount this to the heatsink, you might ask? Stay tuned. No, because I'm not going to do it in this video, but basically I'll show you some tricks. I'll just leave it at that. There's a lot of different tricks to mounting that to a heatsink, surprisingly. You'll be quite surprised. I want to tell you, but I don't want to ruin the fun, so I'll just keep it until we do it. Anyway, that's the fan speed controller sorted out. And I'll just show it in operation one more time now that it's got the final values. Actually, what I'll do is I'll use a 100-degree heat source. I've got the hot air. Let me just show you guys. 100. Alright, after seeing what that voltage went to and how quick, I was going to put a Xena in here and cap the voltage going to the fan, but I've decided to do something different because a lot of fans handle 15 volts, some closer to around 14, but put it this way, if my amp was going over 100 degrees, I would want them to go faster in hopes that it doesn't blow up. And if the thing got any hotter and they stayed on and cooked, the transistors would be getting popped anyway. So there isn't really a need for a voltage limit in this case. The only way that's going to go out of voltage is if the amp's toast anyway. And I mean, if a 500 watt amp is toast, you've got bigger problems than a fan controller. So what I've done is I've gone down another 100 times to 2.2, 10 times to 2.2k from the 22k that was in here. This now gives me a really definitive turning on and turning off position. Keeps them off up to a certain point, and has much faster response. Let me show you. And I get to, complete this circuit using 5 parts. You can't beat that. 1, 2, 3, 4, 5. And 3 of those parts are just resistors, basically. Cheapest transistors, cheapest parts to make this circuit. You can't beat that. So this is still set at 100 degrees. And I'm just going to use my hand to position this and aim it at the NTC. It's kind of tricky aiming it. There we go, I've got it. Oh, now I've got it. It's very hard to get the right angle. And I can hold my finger there that feels like it's about 60 degrees. It's really hard for me to get the position. When I do get it, it comes on straight away. There it is. See, that's a lot more controlled. And look how fast the response is. I reckon that's going to be literally perfect, so I'm going to leave it there. And you know what? When the amp's done, I'll work out the point in its power output that the heatsink gets the hottest, and adjust the value if I need to adjust it. But that's what I'm going with. So I'll make a design on these 2 boards, one for each amplifier, and etch the boards up in the morning. And we'll get on with assembling the amplifier. I haven't worked out what I'm going to do yet because I still got to design the front end for it. So I might etch these boards and put these to the side and do that first, or I might put the amp together and then design the front end for it. I'm not too sure, but either way, that's what I'm doing tomorrow. And then the day after, we'll be testing. So that's all I've got for tonight. I'm done my work for the day. I'm going to leave the video off here. So if you like what you're seeing, give me a like and a sub. And I'll see you all tomorrow in the next video. Thanks for watching.